This is Probability and Measure, Lecture 2. It's time to prove the Carathéodory extension theorem. You see, the Carathéodory extension theorem allows us to start with the idea of a pre-measure, or just a simple set function, on a simple collection of sets. So for example, I might have intervals, and I want to define their length. Well, I can do that, but what else can I measure with this tool that I have here? To figure that out, we're going to use Carathéodory's extension theorem to take that idea of measuring the length of an interval and extending it to an extremely wide variety of sets that we can measure the length of. Let's go check it out in class, because it is freezing cold out here. Welcome back to another lecture of Statistics 571, Probability and Measure. In the first lecture, the one previous to this, what we discussed is really what is a measure, what is a sigma field, some of the basic structures and ideas that we'll need for this course. Now the new idea is, how do we actually construct a measure and a sigma field from something that we know? The idea being that if I want to measure the length of an interval, I can do that, right? I can take the right endpoint, subtract the left endpoint, and I can get the length of that interval. But how do we extend that idea to a proper sigma field, and does it even make sense to extend it? That's what we're going to talk about today. This is kind of a two-part lecture. Today what we'll be doing is something called the Carathéodory extension theorem. The idea is we're going to start with a measure on a relatively small set of sets, and then we're going to extend it to a much bigger collection of sets and show that this extension actually, well, makes sense and is what we want. The lecture following this will be about uniqueness, showing that this extension is in fact unique and that we're not going to be able to extend this one measure, or technically pre-measure, into lots of different measures or whatever. But it sounds a little confusing when I say it out loud, so what we should probably do is focus today on existence. Next time we'll focus on uniqueness. So, to get into the idea of how to construct a measure, we're going to need some more definitions. The first thing I wanted to start with, it was what I said before, which was the idea, right? Because it's always good to have an idea of why are we doing this when you have some crazy esoteric theorems. And the idea is, if the measure, the length, say, of the half-open interval AB is B minus A, I guess for any B greater than A, I guess equal, but then equal would probably be an empty set. So we'll just say for B greater than A, we can measure the length of an interval. Then what else can we measure? Right? That's the idea. The idea is, how can we extend this? And that's what we'll do today. But we're going to need a couple definitions first to make sense of this. So, what do we need? Well, the starting point is to note that the set of all such intervals of the form AB is not a sigma field. So recall from last time, we want our measure to be defined to give the measure is a function, and we want it to give a value to every single set that lies within a sigma field. So we're starting here with just intervals. we have an idea of what their length is, but the intervals do not comprise a sigma field. In this case, I believe they're a semi-ring, and the idea that we want to do is we want to start with this smaller set, the set of intervals, or just in general a ring or a semi-ring, which I'll define in a second, and then extend it to a sigma field. So, what does that mean? Well, what do we need? We need a couple definitions here. All right, so the first thing we're going to need is a definition, and the definition we're going to use is something called a semi-ring. Right, so what's a semi-ring? Well, it's going to be a collection of sets with very specific properties. In this case, we're going to say script A, something that looks, I guess, like that, is a collection of subsets of omega. Remember, omega is our whole space we're working in. It could be the real line or whatever we want. The point is that A is going to be a collection of subsets of omega with the following properties, or I should say is a collection of subsets of omega. A, comma, let's try and do this as a proper English sentence. A, comma, a collection of subsets of omega is called a semi-ring when what? Well, we need a couple things. We need that the empty set is in A. So we have to have the nothing. All right, that's a good starting point. It's like having 0 in your set. Then we also need that for any A and B in script A, then we have A intersect B is also in script A. So that means that if we have two sets in our semi-ring, we're allowed to intersect them and get another set in our semi-ring. So we're allowed to do intersection, you can think of that. Then we have the last bit, which is a little bit harder, a little bit more complicated, and this is following and because I'm saying that for any A and B in script A, we have the intersection, and we also have that B, set minus A, can be written as a finite union I from 1 to n of Ci for Ci in script A. That's a terrible script A, but they're kind of hard to write. So that's a little bit harder to internalize. The idea is that the difference between a B and an A may not strictly, the set difference may not strictly be in the semi-ring, but a set difference can be written as a union of elements from the semi-ring. Right, semi-rings are a little bit harder to work with. I'm introducing them because we just had one in at the above. For the proofs, I'm going to work with rings because they're slightly easier to work with, and a lot of the textbooks seem to prefer working with rings. But strictly speaking, we could look at a semi-ring. The reason why I introduced it is because the set A of all intervals A, B is a semi-ring. You can check this yourself. If we define, well, if A is equal to B, then we can define this as the empty set. And then if for any two intervals, we can look to make sure that their intersection is also half opened, right? I'll just say, check this. So again, we just really would have to go through 1, 2, and 3 and check to say, okay, well, if I have the empty set, that's right away. If I take the intersection of two half-open intervals, do I still get a half-open interval? Yes. That's actually the reason why we work with half-open intervals, because at first you think, well, why are we writing half-open intervals? They're kind of annoying to look at, right? And they're actually super annoying to type in LaTeX. It always wants to autocomplete double parentheses or double square brackets, but in this case you have to manually do it. The reason is specifically for the definition of semiring, right? We can take an intersection of two half-open intervals and we still get a half-open interval. If we just had open intervals or closed intervals, it wouldn't be the case. We would be running into more issues. So the point is we can check these things and show that it makes sense. We can also do set minuses or set differences, and I'm pretty sure that if we do the set difference between two half-open intervals, we're going to get a half-open interval. So the third property of the semiring also holds. Nevertheless, what I want to do, though, is define something slightly easier to work with, which is going to be our starting point for the Carathéodory extension theorem, which is the ring. The ring is going to look a lot like a semiring. A collection of subsets of omega is called a ring when, well, what? Well, we need the empty set again. That's usually a given, that we always need the empty set in our collection of sets. Now we're going to have something slightly different. We're going to say, well, part of it's the same. For any A and B subset, or not subset, element of A, we need that the set difference B minus A is going to be in script A, and we're going to need that the union A union B is in script A. Note that this is a finite union, and this is the union of two elements, and if we were to union it with another one, we could have the union of, say, 3 elements, for example. But most importantly, this implies finite unions, not countable unions. This is important because countable unions would take us to a sigma field. Countable unions require some type of a limit, in a sense. The idea that we can union to infinity and still be within the same set of sets. We don't have that with a ring. We just have finite unions. So the example of a ring is all finite unions of half open intervals. And this is why we can't just consider half-open intervals as a starting point if we're using rings, because they're not a ring, they're a semi-ring. If we allow for finite unions of half-open intervals, so, for example, we might have something like A, B, union C, D being an element of A. Then we have a ring, and that allows us to, well, have a different starting point for Carathéodory's extension theorem. And one other thing, we're going to need, well, we'll include it anyway. We're going to define a field. So the last definition we need is the field, which is basically A is a field if it is a ring, so all of the above hold, and omega is an element of A. So remember, for the definition of a ring, we don't assume that it contains the entire omega. We just assume that it contains, well, besides the specific properties, it contains the empty set. If we include the entire set omega, we now have a field, and the only thing stopping us from getting to a sigma field is having countable unions. Otherwise, we're there, basically. So I'll just put that in as a note. Note field plus countable unions is equal to a sigma field. That's not a real mathematical equation, but you get the idea. All right, and then the last thing we're going to need here is we are going to need the definition of a set function. So mu, a measure, is a type of set function, but a set function is a much more general idea. So a set function is going to be some mu, which is going to take elements of A and give us a positive real value. That's a terrible R. Let's try that again. There we go. A positive real value, or non-negative, because we could get a 0, like for the empty set. But this is not necessarily a measure yet. It's just a set function. I give you a set, you give me a number, right? That's what mu is doing. And it's going to have different properties depending on what mu is. So we'll say, we say that, all right, let me try that again. For, I need sets, right? I need sets first. For A and B in script A, we say that, well, a couple things. First, we say that mu is increasing. So we say mu is increasing if A contained in B implies that the value, I'm not saying measure yet, because it's not technically a measure, the value of set A is less than or equal to the value of set B. So it's an idea of increasing, right? If I have a bigger set, I should get a bigger number out of mu if it's increasing. It doesn't have to be increasing, but it's just a property of a set function. Right? We say mu is additive if, well, for A and B disjoint, that is, their intersection is empty. If A and B are disjoint, then mu of A union B is going to be the sum mu A plus mu B. Cool. Now we're going to take additive a little bit further and talk about countably additive. We'll say mu is countably additive if for a collection of A, I, where I runs from 1 to infinity. By that I mean that it has the cardinality of the natural numbers, it's countable, such that AI intersect AJ is the empty set for all I not equal to J, i.e. pairwise disjoint, then the exact same thing happens that happened above for additive. We're just going to take it into a countable infinity. That is, well, I should say with one more thing, not mu. And the countable union I from 1 to infinity of ai is an element of A. This allows us to apply mu to it because mu only works on sets that are in A, right? So we have to assume that the countable union of the AIs is in A, so that we can write mu of the union I from 1 to infinity of AI. And this is going to be equal to, well, what would it be, right? Above, we said union A and B is going to be the sum of A and sum of B. So this is the same thing. We're going to turn a countable union into a countable disjoint union into a countable summation. If we're allowed to do this, we have a countably additive set function. And lastly, we're going to have mu is said to be countably subadditive if, well, in some sense it's the exact same thing as above, but without the disjointness and with an inequality. So what I mean by that is that if ai I from 1 to infinity are in A, and the union I from 1 to infinity of AI is in A, and I want to emphasize not necessarily pairwise disjoint, then the value associated with the union I from 1 to infinity of this infinite, countably infinite union is going to be less than or equal to the sum I from 1 to infinity of mu ai. So this is the big difference, right? For countably additive, we had a sum. For countably subadditive, we have a less than or equal to, right? And that's the difference, right? And more or less, that's, I think, everything we're going to need in this case. Oh, yes, and we also need the definition of a premeasure. So, often, a set function mu on a ring A such that the mu of, I don't want to say measure yet because it's not technically a measure, the value associated with the empty set is 0, and mu countably additive then we say that mu is a premeasure. The idea is that, if you recall what did we have for a measure last time? Mu was a measure when it's a set function that maps any element of a sigma field into the non-negative reals, such that the empty set gets a measure of 0, and we have countable additivity. If we define a set function not on a sigma field, but on, say, a ring, we often will call that a pre-measure because it's a set function that's almost a measure, but it's not quite there yet. And we're going to get there via Carathéodory's extension theorem, which is the next thing I'm going to talk about. Okay, so the next thing we're going to do is we're going to state and prove the Carathéodory extension theorem. What we need is we need to know what, given a pre-measure, we need to know what the measure that we're looking for is. That's a terrible sentence. Here's the idea. For a pre-measure on some ring A, for a pre-measure mu, it's always mu in this course, unless we're talking about Lebesgue measure, then I will use lambda, but generally mu is always going to be my standard measure that I'm using, notation for measure that is. So for some pre-measure mu on a ring A, we have what's known as an outer measure. New definition. There's a ton of definitions in this course when we get started. Right? We have something called an outer measure. The outer measure is going to be some mu star where it's defined, not on B, I think I was using E in my notes, typed notes here. So mu star is going to take some set E. E is any subset of omega. So we're going well beyond the ring A. We're going beyond, actually, even a sigma field. But what it's going to be is it's going to be defined as the infimum over all, well, I'll tell you what the infimum's over in a second, because it's not, it's hard to write it out in math lingo. So the infimum of the sum over I of mu AI. This is any for any E contained in omega. And I guess technically we could have the entire set omega itself if we really wanted to. So we'll do a, I guess, inclusion there. Where the infimum, the inf, is taken over all collections of AI such that E, the set that I'm trying to get an outer measure for, is contained in the union. Should be countable union, or else does it have to be countable? Yeah, no, of course it does. Otherwise, things just, yeah. I didn't actually define I. It doesn't have to be infinite. It may be finite, it may be infinite, so I'm just going to write the union indexed by I of the AI over all collections. I'm going to say finite or countable collections of AI. So basically the idea is I have a set E. I have no idea. I can't even measure it with mu, but I can outer measure it. And what I mean by outer measure is I'm going to take E and I'm going to cover it with a bunch of A's from my set A, and then I'm going to say, well, I don't know what the measure of E is, but I can cover it in, 27 different sets A that sum up to some value. And that's how we can define a measure in a more general sense. Now, the question is, does this even work for any E contained in omega? So we haven't even gotten to the extension theorem yet. Question: can we measure I guess technically outer measure any E contained in omega. That is, can we assign a value to it that makes sense in some mathematical setting? We're going to look at this more in detail when we do Lebesgue measure and non-Lebesgue measurable sets, but the answer is no. Well, I wonder if there's a case where you actually could measure every possible subset of the power set. I guess if you had a trivial example would be if you had, like from the last lecture when we had a finite collection of points and the counting measure, then you could measure every possible subset. I'm just going to write not necessarily to be vague about it. So what we're going to do is we're going to denote script m to be the collection of all mu star measurable sets. So this is every possible set contained in omega, a subset of omega, that mu star can assign a value to that actually makes some sense. And by measurable sets, we have a strict definition here. Where M to be the collection of all mu star measurable sets. We'll say where we say that E, it is E, right? Oh, B. Yeah, make sure I get this right in my notation. It's very easy to get this backwards. Where we say that B, a subset of omega, is, I guess we can include omega, is mu star measurable when mu star of E intersect B plus mu star of E intersect B complement is equal to mu star E. This is for all E contained in omega. Okay, so that's very abstract. At least to me it feels very abstract. Maybe it makes obvious sense to you when you look at it, but what are we saying here? Well, what we're saying here is that if we have some set B, maybe this is my set B, and we have our entire space, which is going to be omega. So everything outside of here is B complement. So what it's kind of telling us is that for any crazy set we could imagine, E, whatever E is, maybe this is E, then what we can do is we can get the outer measure of E is going to be equal to the sum of the outer measure of the part of E that's contained in B and the part of E that's not contained in B. So it's going to be this piece plus this piece. Right, so if this works for every possible set E, then what we have is we have a set B that is said to be measurable. So in some sense, B is nice enough that we can cut up any subset of omega and the values make sense. We're going to get a little bit more into this when we actually do the Carathéodory extension theorem, and that's the next thing we're going to do. All right, so we get a theorem. It's always good day when you get to do a theorem, and we finally got to do a theorem in this class. It's only day 2. We're going to do a lot of theorems in this class, but this is a big one. So this is the Carathéodory extension theorem. Where Carathéodory gets an accent on the E. Excellent. What does it say? It says simply, let A be a ring on omega. So it's a ring of subsets of omega, and mu A be a premeasure. Then mu extends to a measure on sigma A, which is the sigma algebra or sigma field, depending on which terminology you want to use, the sigma algebra or sigma field that is generated by the sets in A. So we have a couple things to note here. Note 1, sigma of A is the sigma field that comes from extending A by including finite unions. Remember what I mentioned above in this lecture is that a ring, well, I guess including finite unions and omega itself. Remember what I said above, which is that a field is a sigma field but doesn't necessarily have countable unions. Oh, what am I saying? Finite unions. I mean countable unions. Right, so if we have a ring, we need to include omega. Now it's a field. Then we extend from finite unions to countable unions, and we have a sigma field. And that's going to give us, well, a sigma field. And the idea is that what Carathéodory says is that if we have a premeasure mu on a ring, we can extend it to a proper measure on a sigma field generated by the elements of the sets inside that ring. So that's really cool. And the other little thing, the second note, note the correct extension, correct, is the outer measure. So that's why I defined outer measure up above, because what we're going to do is we're not just going to say, yes, there exists an extension. We're going to say this outer measure is the extension that we want. And that's what we're going to prove right now. Okay, so this proof is a little long. It's going to proceed in multiple steps. So we're going to try to break it up into pieces to make more sense of this. So we have the proof of the Carathéodory extension theorem. So the first thing, we assume that B is contained in omega, and that the mu star, the outer measure of B, is going to be finite. If it's infinite, a lot of the things I'm going to say are going to hold trivially, because everything's just going to be infinity is less than infinity is whatever, less than or equal to infinity. So we're going to assume that the outer measure of b is finite, but of course, if we really want to be precise, we'd have to go back and check the whole proof for if the outer measure of b is infinite. It's just not very interesting, so I'm going to skip it. But we can do it if you really want to. Right. So then, step 1. Which is going to be prove stuff about mu star. Okay, so the first thing we need to do is we need to see if mu star is actually going to be a measure, right? We have a pre-measure, which it's basically almost there, right? We just need to be able to extend our pre-measure to a sigma field. Mu star is defined on the entire all possible subsets, but we want to find the right sigma field to define it on. Like, there's a bunch of stuff going on. But first of all, we just need to we need to learn some things or prove some things about mu star. So the first thing we have to note is that mu star of the empty set is 0, right? As mu is a pre-measure. And as we said above, if we have a pre-measure, it means that we assume that the value assigned to the empty set is going to be 0. Next thing, mu star is non-negative for all b contained in omega. So right from the start, we don't strictly know that it's a non-negative function, but it comes very fast from the fact that this is, I'll say, as mu is non-negative, and of course mu star is just an infimum over a sum of mu's, right? That's what we said up, where is it? Up here at the top of the page, right? Mu star is just going to be the infimum over a bunch of sums of mu's, and since mu can't be anything smaller than 0, neither can mu star. So we know that it's non-negative. We know it assigns 0 to the empty set. Those are all good starting points. A lot of the proofs we'll be doing are just going to be checking a bunch of stuff. So the first time you do them, they're kind of fun. Then they become a little tedious, and you're like, yeah, we just got to check everything again. Anyway, yep, so we have that. What's next? Oh, yes, mu star is monotone. So what we mean by that, I guess in this case, I think I used above, I said it was increasing. I think I changed my... above I said a set function is increasing, and here I wrote monotone. But what I mean by this is that, let's say let's, I guess, mini prove it, right? Let B1 and B2 be elements of a ring, and assume that B1 is contained within B2. Then, for any collection AI such that B2 is contained in the union of the AIs, and I guess strictly speaking then B1 also has to be contained in the union because it's contained within B2. Yeah. Then B1 is contained in the union of the AIs. Therefore, the outer measure of B1 cannot be any larger than the outer measure of B2. I don't think I wanted B1 and B2 to be an A. I think I just wanted B1. I'm going to correct this. I think I just want them to be subsets of omega. Right? For any two sets that are subsets of omega, if one is contained in the other, then I know that the covering, if I covered the bigger set, I've necessarily covered the smaller set. Therefore, the infimum over all sets that cover the smaller set can't possibly be any bigger than the one that covers the bigger set. Hope that kind of makes sense. You could just imagine as I have B2 and I'm covering it with a bunch of pieces, I've already covered B1, and the infimum can only get smaller if I have a smaller set then, thanks to how infimums work. All right, we've got one more fun little property of mu star to prove, and then we'll move on to part 2 of the proof. So mu star is countably additive. A very important property if we want to make it a measure. Okay, so let's check that. For, let's say bi, I from 1 to infinity, where I guess bi is just, typically what I'm trying to do, and I'm going to see if I can be precise about this, sets B are going to be subsets of omega, and sets A are going to be within the ring A. Trying to keep that as consistent as possible, but sometimes the notation gets away from me, so we'll see if we can do this. Anyway, let's say we have a collection of sets B and a given epsilon greater than 0. Always a good day when you get an epsilon greater than 0, right? Then we're going to say let bi be contained in the union over J of, the union of J of the aij's for aij in script A, the ring. So the point is we have a countable collection of bi's. We're going to cover each of these bi's with some aij's, where j is going to be some countable index, possibly finite. Such that, so we're covering it in such a way that the sum over j of the measure, or the pre-measure, I guess, mu aij is going to be less than or equal to the outer measure of bi plus epsilon 2 to the minus I. Why can I do that? In this case, we have an infimum, right? We have that mu star of bi is an infimum, which means that in some sense it should be, right, less than or equal to the sum of the measures of any possible covering aij. In this case, what we're doing is we're taking that infimum. Remember, infimums are kind of like touching they're right at the lower bound where it touches. So we're taking that infimum and we're adding just a little bit, epsilon divided by 2 to the I. And what it means is that we can kind of reverse the inequality. So this happens a lot when you're dealing with sups and infimums in real analysis, right? You can kind of shift the infimum up a little bit and then reverse the inequality, then take epsilon to 0, and that's what we're ultimately going to do. But we're not there yet. We're almost there. So that's the first step. Then next is as the union, the countable union I from 1 to infinity of the bi's is contained in the also countable union, double index but still countable, of the aij's, and as mu star is monotone, as we already, increasing that is, as we already proved above, and mu is subadditive. And mu, okay, not mu star, mu, the pre-measure, is subadditive. Then what are we going to do? Well, again, what are we trying to show? We're just trying to show that it's countably additive. So in that case, if we sum up a bunch of these BIs, if we union a bunch of the BIs, we get a sum of the bunch of the values, the measured BIs. Countably subadditive. I made one mistake here. Sorry. I'm trying to prove countable sub-additivity of mu star, not countable additivity. Subtle difference. I mean, you could probably do additivity if you made the BIs disjoint, but I'd have to think about that for a second. Regardless, the point is we're trying to prove countable subadditivity, so all I want to do is show that the union, that's what I'm going to start with here, the outer measure, mu star, of the union I from 1 to infinity of the BIs, I want this to be less than the sum of the outer measures of each of the BIs, but how do I get there? Well, the first thing I'm going to do is say that this is less than or equal to the measure mu, or the pre-measure mu, over the double union ij of the aij's. Because remember, the aij's cover this whole set, and by the definition of the outer measure as an infimum over all possible covers, then we have this relation here. And because we're working on A, the ring, we're allowed to go from mu star back to mu. And that's nice, right? Because mu is better to work with than mu star. So what we're doing is we're trying to push our way back to mu, work within mu, and then jump back up to mu star. Anyway, this is the first step. The next step is we use the countable subadditivity of mu to show that this is now the sum ij, or less than or equal to the sum of mu of the aij's. Then we're going to use then what we're going to do is we are going to jump back up to the b's here and say that this is going to be less than or equal to the sum, let's see if we get this, oh yes, over I of mu star, the outer measure, bi plus epsilon. This last line is coming from this thing that we did earlier. What we're saying is that if we sum over all the j, then the sum of the measures mu of the aij summed over all j is going to be less than or equal to mu star bi plus epsilon 2 to the minus I. If I sum up 2 to the minus I from I guess 1 to infinity, I get 1, which leaves me with an epsilon down here. And then we do the nice little final bit, which says basically take epsilon to 0 to get that mu star is countably subadditive. So that's roughly the idea, right? It's kind of neat what we did, right? We don't really know how to work with mu star. So what we did was we went from mu star back to mu. Mu we can work with, then we went back to mu star at the end, and then we basically had an extra epsilon floating around, but epsilon is arbitrary. Take epsilon to 0. We've got our countable subadditivity for mu star. Okay, what's next? That was just step 1. Step 2. of the proof of the Carathéodory extension theorem is that we need to make sure that check that mu and mu star coincide, give me the same number, that is, for all A contained in the ring script A. So what we want to do is we just defined this idea of an outer measure. Is it consistent in the sense that it gives me the same value as mu? So we actually have to check this, right? It seems like it makes sense from the definition. I mean, the definition is kind of like, yeah, okay, sure. It's probably going to give me the same thing, but we have to be precise and actually check this. So how do we prove this bit? Well, we say for any A contained in the ring A, we have, like, immediately the trivial way to say it, I hate that, but the easy way to do it is, the easy direction, that is to say that mu star of A has to be less than or equal to mu of A, because, simply put, A is a subset of A, and since mu star is the infimum over all possible subsets, it can't get, and the measure, the mu star of A, can't be any bigger than mu of A. So that's the first direction. Now we're going to try to prove the reverse inequality to show that mu star of A is actually equal to mu of A. So for the reverse, what are we going to do? Well, what we're going to do is we're going to say if A is contained in the union I from one, well, forget it. I'm just going to write I, and what I mean by that is I could either have a countable union or I could have a finite union, but I'm just going to write union over I of the AI. Then, by countable subadditivity and monotonicity, or the increasing property, what do we have? Well, we have that the measure, pre-measure mu of A is less than or equal to the sum of mu A intersect with AI. Right? So that's the first step. Why is that true? That's going to be our countable subadditivity. The point is the union of A intersect AI over all I is just going to give me A again, because A is contained in the union of the AIs. Hope that makes sense when I say it out loud. So that's countable subadditivity. Then we're going to use the monotonicity property to basically just throw out A and say that this has to be less than or equal to just the measure mu of AI. So what does that tell us? Therefore, that means that the measure mu has to be less than or equal to mu star of A. Why is that the case? Well, that's the case because I've basically showed that for any covering, for any collection of AIs that covers A, I know that the measure of A, mu of A, has to be less than or equal to the sum of the mu of the AIs. And since I'm taking the infimum over the whole thing, it could possibly be equal, but it can't be any less. So then we put these two together and we show that mu of A is equal to mu star of A for all A in A. I like how for all is an upside down A here. Very nice. Okay, so that's step 2 of Carathéodory's extension theorem. We know that mu star has some nice properties, step 1. Step 2, mu and mu star coincide on the ring. Now we need to actually extend this thing. All right, so step 3. Step 3 is that we want to check that the ring A is contained within M, where recall that, well, A here is the ring that we're starting with, and M is all mu star measurable sets. So what this means is we want to make sure that, well, I'll say i.e., I'll just write it all out. For any A in A, we want to show that A is mu star measurable. All right. So I guess i.e. again, double i.e. We want mu star of E to equal mu star of E intersect A plus mu star of E intersect A complement, and this is for all E subset of omega. All right. So how do we show that? Basically, we want to show that every element of the ring is mu star measurable. How do we show that? Well, the first thing we note is that, so first we note that mu star of E intersect A plus mu star of E intersect A complement has to necessarily be no smaller than mu star of E. Why? This comes from part 1, and part 1 of the proof is to show that mu star is subadditive. So we showed that mu star is subadditive, therefore this one way has to work. Now we want to prove the reverse inequality so we can conclude this little mini part of the proof here. So for the reverse, so maybe I'll just say next. And we're going to do something kind of similar to like what we did before. I'll show you. We'll say for some epsilon greater than 0, what we do is we choose a covering AI such that E is contained in the union of the AIs, and we do that same little infimum trick that we did in the previous part, where we say that the sum of the measures of the AIs is going to be less than or equal to mu star of E plus some epsilon. So we're saying that we can go to the infimum, add a little epsilon, and we have this covering here. That's the point is the covering AI is really, really close to mu star of E. We'll say furthermore, we have two more things here, which is that E intersected with AI, or not AI, sorry, E intersecting with A is going to be contained in the infinite intersection, countable intersection of A intersect A I. Right? Because what are we doing here? We're basically saying, do I want countable intersection? We're saying here that A, let's make sure this actually makes sense the way I wrote it. A is some set that we want to show that it's measurable. E is any possible set. We know that the AIs cover E. Therefore, if we are intersecting a bunch of... Yes, I guess this does... We also have the reverse one down here, which is this A complement is contained in the infinite intersection of A complement intersect AI. I guess this is because... See, what's confusing me about this is that E should be contained in the union. Oh, I think this is going to come down to the fact that if I intersect A with a union of the AIs, then that would be like... Wouldn't that be unioning the intersection, not intersecting the intersection? Let's look at that for 1 sec. All right, yeah, so I made a slight typo here in my notes, which was confusing me. We don't want a countable intersection. We want a countable union here. That makes a lot more sense. The point being that E is covered by the union of the AIs. So if you think about this, on the left-hand side, we have I'm in the intersection of E and A if I'm in both E and A. On the right-hand side, I have to be in A, and I have to be in at least one of the AIs to be within the union. So I could actually be slightly outside of E, depending on how the AIs cover E. Anyway, we got our unions now, our countable unions. Good. And that's what I want. Because now we can come quickly to the end of part 3, or step 3 of this, and say, thus, what we have is that the measure, the outer measure, mu star E, intersect with A plus mu star E, intersect with A complement, is going to be less than or equal to what? Well, again, I have a countable union here that's covering it. So what I'm going to do is rewrite this by subadditivity as a sum. But now I'm working with just sets A intersect AI, which live in the ring, so I can get rid of the star, right? Whenever I jump back to only working inside the ring, I can turn mu star back into mu, which is nice. Because now I just have this sum of a whole bunch of elements that lie within our ring. And where's my complement? I guess A, not AI, is supposed to be complemented. Cool. Because if we look at this thing, well, what happens if we sum this all up? Well, these are all going to be... Well, I guess if you take one element from the one sum and one element from the other sum, they're disjoint, and by additivity, we end up with a sum over I of mu AI. And if we sum all that up, we know that this has to be less than or equal to mu star of E plus some epsilon, because that's what we did way back up with that little infimum epsilon trick. Again, just to reference, it's this thing, right? We use that little trick to move from mu back to mu star, take epsilon to 0. And we're done with this piece. All right, so we're almost there now. We have part 4. Part 3 was just showing that everything in the ring is measurable. Step 4 for our proof. This is actually going to end up being a pretty long video. I figured these would just be short little, like, let's prove a theorem videos, but yeah, this one's going to be a bit long. That's okay. It's good stuff. The last big thing we have to do is show that M is a sigma field. We have the set M of all possible mu star measurable sets. We don't know a priori that it's a sigma field. Seems reasonable, but we don't know that it is. We got to check that, and we're going to check it basically by just checking all the definitions, all the properties of a sigma field. So again, not the most interesting thing to do. We're basically just checking off boxes until we can say, yep, this thing's a sigma field. So what do we need to do? Well, first thing we need to do is show that the null set is in M, because, well, simply put, I should say the null set, the null set is in M since whatever, the null set is in the ring, and we know that the ring A is contained within the measurable sets M. Rings don't necessarily have the entire thing, omega. A sigma field has to have omega in it, and in this case we can show that it does, since for any E contained in omega, I guess it could be itself, that'd be kind of a strange thing, but that's okay. Since for any E in omega we have that mu star of E intersect omega, which is the whole just E, plus mu star of E intersect omega complement, which is the empty set, is mu star E. So yeah, basically we're done with that one. We know that we have the empty set, we know that we have omega, the whole thing. Next, since by De Morgan's laws, or rules, or whatever it is, we know that the intersection A intersect B can be written as A complement union B complement complement. If that's confusing, I would try to draw out a Venn diagram. It can sometimes help, and you think, well, A intersect B is the middle of the Venn diagram, and here we have A complement, everything not in the A circle, B complement, everything not in the B circle, and then we union it, and then we complement it again to get the intersection. So you can kind of try to visualize that. But anyway, because of that, we will show that M is closed under intersections All right, so how do we show that? Well, for B1 and B2 contained in M, they're both mu star measurable, and any arbitrary E contained in omega, a subset of omega, I should say. What do we have? Well, we have that mu star of E is going to be mu star of B1 intersect with E plus mu star B1 complement intersect with E. What we want to show is we want to show that the intersection of these two things is also mu star measurable. So that's what we're going to do. We're going to try to basically build this whole thing up. So what we're going to do is we're going to now intersect again and get, it's going to get a little messy. We're going to get B2 intersect B1 intersect E plus mu star of, let's make sure we get all these right, B2 intersect B1 complement intersect E plus, we still have a mu star B2 complement intersect B1 intersect E. And lastly, to round it all out, B2 complement intersect B1 complement intersect E. Cool. Okay, we can lower bound this. Yes, we can lower bound this by doing what? Basically combining the last three guys together. So we're going to take, I can change the color here. Let's try that. We're going to take this one, and this one, and we're going to put them all together and use subadditivity in reverse to show that this becomes mu star of B2 intersect B1 intersect E plus, and now this is going to be kind of tedious to look at, but it's going to be mu star of, and now we're going to have a couple things all union together. B2 intersect B1 complement intersect E unioned with B2 complement intersect B1 intersect E union with B2 complement B1 complement intersect E. Whew. All right, we got that. What is that equal to? Well, that is equal to mu star. And then we're going to write this as B2 intersect B1 intersect with E plus mu star B2 intersect with B1 complemented using what we talked about before, intersected with E. And this, by subadditivity, yet again, has to be less than or equal to the outer measure of E. But that means we started with E, the measure mu star of E. We ended with mu star of E. Therefore, everything here is equal. And that means that this guy, the second to last line here, has to equal mu star of E. Which means that the intersection is mu star measurable. Therefore, B1 intersect B2 is an element of M for any B1 and B2. So we've got our intersections. Cool. Now we're going to need to do, what's the last bit? Oh, we need countable unions, right? Like I said, it's just a lot of checking everything. So lastly, maybe I'll put a bullet point here. We note that B minus A is equal to B intersect A complement. Therefore, we need to show that M is closed under complementation so that follows from the definition this is, for lack of a better word, it trivially follows. This is because mu star of E intersect B complement plus mu star of E intersect B complement complement, which is just B, is going to be mu star of E. So the point is that if B is mu star measurable, then its complement is mu star measurable, and since it's closed under intersections, we can intersect B with A complement, and we have something that's measurable, and thus B set minus B minus A, or B set difference A, is going to be mu star measurable as well. Whew. All right. So what we've got is we've got a field. But we don't have a sigma field yet. So let's write that down. Therefore, M is a field. But now what we want to do is we want to extend this to a sigma field. So we have one more thing to do, and then we'll be done with part 4, and then I think we're just about done. Yes. So, to get to a sigma field, well, what do we need? Well, let the collection Bi in M. So I have a collection of mu star measurable sets. Let this be, I think I want, countable, of course. And pairwise disjoint. All right, so we've got B. They're all measurable, they're countable, and they're pairwise disjoint. And we also need the countable union I of the BI's to be in M. All right. Now we're going to say let B, we're going to define B to be equal to this countable union. I'm just going to write I from 1 to infinity of the BI's. And then we're going to do kind of the same thing. We're just going to jump right into the definition. Therefore, what do we get? Or maybe not therefore, there's really no therefore here. I'll say then, let B be that union. Then what do we have? Well, we have the measure of the outer measure of some arbitrary E can be written as the outer measure of E intersected with B1 plus mu star E intersected with B1 complement. Okay. Then we're going to take B1 complement and we're going to do it again. So we're going to leave the first guy here untouched. And then we're going to take the second guy and we're going to say, well, the measure of E intersect B1 complement is going to be written as two things. It's going to be mu star I feel like I need, yes, E intersect B2 plus mu star E intersect B1 complement intersect B2 complement. Oh, yes, of course, because they're pairwise disjoint. I was trying to figure out why in the world I don't have a B1 here. Why is there no B1 there? There's no B1 complement there because B2 is necessarily contained within B1 complement because they're pairwise disjoint. Good. I was worried something was wrong there. I'm like, what happened to my B1 complement? The point is, it's pairwise disjoint. Don't need it. Anyway, we just continue this pattern. And what we end up with is something like mu star of E is going to be the sum I, finite sum, 1 to n, mu star E intersect bi, and we're going to have one extra little piece at the end, which is going to be mu star E intersected with the intersection I from 1 to n of bi complement. All right. So now we're going to apply monotonicity, subadditivity, and we're going to take n to infinity. Then, by monotonicity, subadditivity, and m going to infinity, n, what am I saying m for? It's a long lecture. N going to infinity, we get that mu star of E has to be less than or equal to, well, the sum I from 1 to infinity of mu star E intersected with bi plus mu star E intersected with B. Remember, B with no subscript is the union of the BI's, the complement of this thing, which is the same as the intersection of the complements is the complement of the union, I guess. Right, so we have that by which? I guess in this point they all have to, I guess monotonicity would be this one. Then by subadditivity, because it contains it. By subadditivity, what we're going to get, and all the BI's are disjoint, of course, so this makes sense. By subadditivity, then what we're going to do is we're going to replace that big sum with just a mu star E intersect B plus mu star E intersect B complement. But this, again, has to be less than or equal to, oh, I guess, yes, yeah. This has to be less than or equal to mu star of E. So these two things are the same, therefore everything's equal, and we're done. We have that M is closed under finite, or under countable unions. Is closed under the operation of countable unions. Almost there. Therefore, oh yes, and we can, yeah. Therefore, well, it's almost a sigma field. I guess what we can do is we can choose E, the arbitrary E equal to B, and therefore the outer measure of E is just going to be the sum I from 1 to infinity of mu star E intersect bi. So what did we get here? Well, we got two things. One is we got Well, we have mu star is countably additive. I think before we only had countably subadditive. So we have this, and up here we have that M is a sigma field. So we have a countably additive function on a sigma field. We have a measure. So that's basically the conclusion. What we have is that mu star is a set function. Well, let's write this all out. The conclusion of the proof. The conclusion is that mu star is a set function that takes any element of the power set of omega into the non-negative reals. But it's also a measure on M. And since A is contained within M, the ring that we started with at the very beginning is contained in the set of all mu star measurable sets, then necessarily the sigma field generated by A is going to be contained, possibly strictly, but we'll just leave it like this, I think. Well, maybe I'll write it, I guess, precise, possibly strictly, or not. The sigma field generated by all of A is also going to be contained within M, because remember, that sigma field is the smallest sigma field that contains A. M is just some sigma field that contains A. And then lastly, as mu star is a measure on M, it is also a measure on sigma A, which is what we were trying to show at the beginning. All right, so we did it. We took our measure mu, our pre-measure, on a ring A, and what did we do? Well, we extended it to the entire sigma field generated by A. We actually extended it further. We extended it to all possible mu star measurable sets. But that could be, and actually often is, very slightly different than what we would get then. Well, let's see. Yeah, we got like 2 minutes before my camera dies of battery. So what we'll say is that, note, M, well, sigma A may be strictly, I'll say sometimes, not always, sometimes M is going to be actually bigger than sigma A. A good example of that is going to be Lebesgue measure and something called the Borel sets or the Lebesgue measurable sets. They're slightly different, and we're going to talk about those, but I think at this point we'll save that for another lecture. So thank you so much for listening, and see you in the next one.